Buffer solutions function to limit changes in pH. If quantities of acid or base are added into solution. Buffer systems do not prevent changes in pH. They just limit changes in pH because of the common ion effect. So that means that buffer solutions function with common ion effects. So we have to make a solution that contains a common ion with a weak electrolyte, weak acid or weak base. And in that combination, if you add excess hydronium ions or excess hydroxide ions, you'll find a much smaller shift in pH than you would if you had a solution and just poured acid on it. Acetic acid, and you put HCl in it, it would be a large shift in pH, or a lot of sodium hydroxide, a large shift in pH. But in buffer solutions, it'd be a very small shift in pH. So the composition of a buffer solution is a weak electrolyte plus the salt of weak electrolyte. For example, if we made an acidic buffer, might be acetic acid and sodium acetate. So you see it's a weak acid and the salt of that weak acid. Or an alkaline buffer would be something like an ammonium hydroxide and ammonium chloride, because the common ion effect would be function along with the base to shift the pH very little. And what I want to show you in this presentation is one calculation of buffer pH. I want to show you calculation of pH after adding excess hydronium ions and, of course, hydroxide ions. Now, buffer solutions that I'm about to present to you is very basic concepts. But buffer solutions can get very involved in the more advanced work. Buffer solutions, you have what they call tris buffers, and you have complex phosphate buffers, and it goes on and on. So what I give you is the basics and is consistent through whatever the complexities are, but they can get very involved in the formulation of buffers. Start with the buffer solution pH. We want to make a buffer and then look at its pH effect. Okay, so it has to consider, we'll start with an acidic buffer, and so you're going to mix say a 0.20 molar acidic acid aqueous plus a 0.20 molar sodium acetate aqueous solution. Now this is 0.2 per liter, 0.2 per liter, so you pour them together, you get a couple of liters, okay? But what we're going to do is say when you mix these two 50-50, they're the same concentrations, what do you get? Well, you cut them in half. So this is going to give you a 0.10 molar, as you double the volume, 0.10 molar HOAC NaOAC buffer. This is when both of the ion concentrations are identical, and this is called a 50-50 buffer. So we're saying that we mix this together, and here's our buffer solution, and the buffer solution concentration is 0.1 molar. Okay, so the analysis of buffer solution always starts with the weak electrolyte equilibrium. So what's the weak electrolyte in our buffer system? Well, it is the acetic acid. Remember at the beginning of the lecture I said, well, the phraseology of weak electrolytes refers to weak acid and weak bases. So in the problem, you're given a weak electrolyte, you look for the acid or whatever the base is. So you start with the weak electrolyte equilibrium reaction. So what that would be is HOAC going to hydronium ion and the acetate ion. And you treat it as if it were a common ion effect and calculate the pH from that. So what do we need for pH? Of course, the hydronium ion concentration. Okay, so I'm going to set here. So we start with Ci, changing C at equilibrium. So we know we have a 0.10 molar acetic acid, but we also have a 0.10 molar in OAC, and we call it our 50-50 buffer. And so we start the system initially with no hydronium ion generated. It hadn't ionized yet. So decreased by X, and that's 0.10 minus X, and of course that is 0.10 molar here. And so this one is plus X, and that'll give you X, 0.10 plus X, and that is 0.10 molar at equilibrium. Of course, it's the equilibrium row that we want to plug into the Ka expression. And so we use the equilibrium of the weak electrolyte and substitute our values. So we have the hydronium ions, what we're looking for, and then we have 0.10 molar here and 0.10 molar here. And that's 1.8 times 10 to the minus 5 for the Ka value. And that's a given. course. Now, what we're talking about is a 50-50 buffer. Now, this is a unique situation for when the acid or weak electrolyte equals a salt concentration. If you're talking about an acid buffer, for a 50-50 buffer, notice how the salt and the acid will cancel out of the Ka expression. And so the hydronium ion is equal to the Ka value. So you can have a kind of a sub-rule here for all 50-50 buffers. Let me move it up here like this. Acidic buffers, of course, we're looking for the hydronium ion concentration always equals the Ka value. For alkaline buffers, of course, the hydroxide ion concentration would be Kb. Now, this is for a 50-50 buffer. That is when the salt and the weak electrolyte are equal. You can do that. So this is one of the reasons I gave you the sheet here and the handout. So if you look at this handout that I gave you that's the acid ionization constant on it right here. You can make just any buffer you want, any 50-50 buffer, and calculate immediately the pH of that buffer by taking the minus log of whatever the Ka value or the POH and use the minus log of the Kb. And so looking at this, let's see if we can squeeze out some Ka values. So there's the first one up there's acetic acid. You can see that one, hopefully. So I'm trying to get a better focus here. A little better. So acetic acid has a Ka value of 1.8 times 10 to the minus 5, the one we're working on. So for a 50-50 buffer, what would be the hydrogen ion concentration? Well, 1.8 times 10 to the minus 5. Okay, now what's the pH? Log of that. So that's all you have to do. So to make a long story short, a 50-50 buffer, we'll do that one real quick for you. 1.8 times 10 to the minus 5, and it's a minus log, of course. I'll just hit the log button. So it looks like and we changed our sign, 4.74 or 75 is the 50-50 buffer. Now, of course, this is a unique concentration relationship for that buffer. Okay, so with this as the hydronium ion concentration, because those two cancel out, then we can get the pH to equal minus log of the hydrogen, which equals minus log 1.8 times 10 to the minus 5, and that comes out 4.75. So you have an acidic buffer. So you can do the same thing with an ammonium hydroxide and ammonium chloride buffer. Make them 0.1, 0.1, and same thing. The POH will come out 4.75 also, because the Kb value is 1.8 times 10 to the minus 5. Then you can subtract that from 14, get the pH value, which is up in the base range. It's called the Henderson-Hasselbalch equation. Now this Henderson-Hasselbalch equation is used for calculating pHs of buffer solutions when 50-50 buffers, as well as buffer solutions that the conjugate base or counter ion, it doesn't equal the concentration of the weak electrolyte. And the Henderson-Hasselbalch is derived out of the Ka expression for a buffer solution. But it looks like this: pH is equal to pKa plus log of the base concentration over the acid concentration. So if you have, this would be, say, the conjugate base of the system, and this would be whatever your acid is. Now, you can use this same one for alkaline systems, and that'd be a pKb plus log of the conjugate acid. This is a conjugate base, the anion concentration, a log of the acid over the weak electrolyte base, where this would be the conjugate acid concentration, and this would be a cation concentration. And using that. So the simplicity of this is, given the concentrations of the salt and the acid, you can calculate the pH of that buffer solution. Now, one little nuance in this is to do with the pKa and the pKb. The K, pKb, A, or in the whatever pKb should be plus or minus 1 of target pH. And that is, when you calculate, you're looking for a certain pH right here. You have, say, a Ka value to equal 1.8 times 10 to the minus 5. Well, the pKa is going to be the minus log of that. And I believe that 4.75. So what this tells you, you got this, what your buffer solution should be is plus or minus 1 of this. So your pH is equal to 4.75 of your buffer plus or minus 1. If I can draw a 1 instead of a dash, that is, whatever you prepare should be within plus or minus 1 of this pKa. So that would subtract 3.75 to 5.75. So your buffer system is going to be in that range somewhere based on the base. Now, if it gets outside of that, it's what we call a non-conforming buffer solution. You'd go to some other kind of combination that would give you a reasonable acid-base combination. That's when it starts getting kind of complicated in the preparation of buffer. Okay, so the idea of what's the pH of the buffer mix? Well, you use the Henderson-Hasselbalch equation. And so it's just a matter of taking the data and plugging it into this. But you have to have the pKa first, which is minus log of 1.8 times 10 to the minus 5. So when you're given something like this, be sure to minus log it anyway. And so that's 4.75. So that's what goes here. And then your concentrations are substituted in here, and you grind out the answer. So pH is equal to 4.75 plus log. Well, the base concentration would be this, because you're just going to ionize to deliver the OAC as a conjugate base in the system right here. So that would be 0.085 molar. Molarities will cancel out over 0.055, and so that gives us I'll string it out. Like that. Now, there's another meaning in here, 1.55. When you look at this, this means that the base concentration is 1.55 times greater than the acid concentration. Or it also means 1.55 over 1. This is your conjugate base, and that's your concentration of your conjugate, or your weak acid. And I'll show you another calculation out of that that you'll need later on to understand how this is used right here and why it's important. Okay, so 1.55, we take the log of that, so it gives me a 0.19. And so that's 4.75 plus 0.19, and of course plus 4.7. And so when you test your buffer, it should be 4.94. So really the whole process here is to show you that not all the buffer systems are 50-50 buffers. Now that'd be great if we could do that, but that's not necessarily the case. And now what this shows you is that the conjugate base is 1.55 times more than the acid. What you can use that to calculate is the mole fraction of each component in the buffer. You remember mole fraction is the moles of ion, say, over the sum of all moles. And it comes out at decimal fraction. So what we're looking at here is moles of base is equal to 1.55. Moles of acid is equal to 1.00, with the total moles to equal 2.55 when you add them together. So the mole fraction of base, which is the OAC in this problem, is 1.55 over 2.55, and the mole fraction of acid, and you'll need this in preparation of buffers, 1.00 over 2.55. It's 1.55 divided by 2.55, and that's 61%, or 0.61, and the other one's 0.39. So what these are kind of like percentages, but they are left in fraction. That is, 61% of your solution is the conjugate base. So you have a high conjugate base concentration and a lower acid concentration. And so that will be used shortly in buffer preparations. But where did I get that? Look at what I did up here is I took this base over acid ratio from the Henderson-Hasselbalch and reduced it or normalized it so that it's actually 1.55 over 1. So I divided that into that and got that and that. That's all I did. When I add them together, that's of course the sum of all the moles, because that's what it is, the mole concentration. And so part over total, each one, gives you those mole fractions, and I'll show you how to use that here in a few minutes. Okay. I'm going to go ahead and write a buffer solution. We're going to use a 50-50 buffer. That is 0.10 molar in HOAC and 0.10 molar in the acetate ion. One, calculate pH of buffer before adding H plus or OH minus. 2, calculate pH after adding 0.01 molar hydronium ions. That can become from HCl or wherever. And 3, calculate pH after adding 0.01 molar in hydroxide, maybe from sodium hydroxide, wherever, strong base, regardless. One, pH of the buffer, of course, Ka, or the hydronium ion concentration, is equal to the Ka value, which is 1.8 times 10 to the minus 5, because we have the 50-50 buffer here, as we've shown you. So pH is, of course, minus log of that 1.8 times 10 to the minus 5, and that's 4.75. So what we're looking at in problems 2 and 3 is how does the addition of the H plus affect that 4.75, or how does the addition of an OH affect 4.75? How much change does it force on the buffer system? You're going to add 0.01 of hydronium ions. To our 50-50 buffer. And the pH is going to change. And what did I tell you a little while ago about in starting buffer problems, you always start with the equilibrium of the weak electrolyte, right? And that's what we have to start with. Well, this is a HOAC buffer with acetate ion in the system. And our buffer initially is 0.10 molar in the acetate and the acid, like this. And essentially, we're going to say that, well, we have 1.8 times 10 to the minus 5 molar in the hydronium ions. So what we're looking for is this new pH, a new pH after throwing in and removing the hydronium ions. Well, it starts here. Now, for general purposes in working these problems, what you need to do is simply assume this is 0. Because that's really where you're going. You're going to add the acid, and then the reaction is going to shift in order to establish a new equilibrium by applying changes. So what you're going to do is you're going to add a 0.1 molar hydronium ion to it. Now this is where it gets tricky. Everybody listening to me carefully. So let's look at this from a seesaw standpoint. You have an HOAC, an equilibrium, with hydronium ions and the acetate ions. There's your buffer system right there. Now, what happens if you add hydronium ions to that? Which side collects or gets heavier? The right side. So the outcome of adding the hydronium ions is to tilt right. Everybody agree with that? Everybody see? So what that means is we've destroyed the original equilibrium, and the reaction has to shift to reestablish it. So which way is it going to shift? To this way. Yes? And so what's going to happen to the concentrations on the product side? If the chemistry is what you're doing is removing this excess by this shift. So this excess is going to shift from right to left as long as you have the unbalanced or excess hydrogen. And it keeps shifting until that excess is gone and you establish a new equilibrium down here. So the shifts left until new equilibrium is established. That's how buffer systems function. So it shifts and we make a new equilibrium with new concentrations. Now, how do you determine what the new concentrations are? I'll show you that. With new concentrations. Now, to this point, does everybody understand what the natural trend is? I mean, what happened, okay? Now, if we add the excess, okay, that's what this is all about. You know, we've got this, and then we throw in the 0.101, sorry. 0.01 molar in, say, HCl is something like that. Okay, it got this side heavy, then it shifted. Now, looking at the concentrations, if it shifts from right to left, what's going to happen to the acetate concentration? It's going to go down from where it started. See, this is in excess right now. So this one's going to go down, and this one's going to go up to give the new equilibrium. Now, this is how that's dealt with in the ICE table. Let me show you this. Let me rewrite that ICE table. I'll leave that much up there. Okay, so we have an HOAC, H plus the acetate ion, initially 0.10. We'll say that starts at 0, and 0.10 molar in each of those. Now, what are the changes? It's got to change to remove that excess hydrogen. We put in 0.01 molar. That got to be taken out. So what happens? I showed you this goes down by the amount of acid removed. So in the change row, you subtract 0.01 molar. That's what's happening. You are removing that excess here by combining with the OAC and shifting over here. Now you have a 0.01 molar higher HOAC. So you come over here in 0.01 molar. Now, then you disregard what's in the middle here and go, your new equilibrium has a 0.11 molar in HOAC, and X is what the new hydronium ion concentration is. Not going to be the Ka equal now. And so this is 0.09 molar now. So it's this row you reapply to the Ka expression, solve for X, and you've got your new pH. And you compare it to the 4.75 we started with. See which way it goes, okay? So this is your tilt. This is tilt right, shift left. When I do the OH, you'll see it go the other way. See? Okay, so Ka is H OAC over HOAC. And so that's 1.8 times 10 to the minus 5. Still have to use the same Ka value. Okay, we're looking for the new hydronium ion concentration. And so now our OAC has gone to 0.09 molar. And that's divided by 0.11 molar for the new concentration of acetic acid. So when we solve for the hydronium ion nu, it would be 0.11 times 1.8 times 10 to the minus 5 over the 0.09. All that's in moles per liter. And once you get to the hydrogen, you go to minus log and you got it. Got the pH there. So 'So there's your new H plus once it shifts into the new equilibrium, and the pH nu, after it takes out all the excess, is minus log of that. .65. We started equals 4.75, and you went to ending pH of 4.65. That's not much of a change. That's the idea here. Now, one of the things you want to notice about what happens to a buffer if an acid is added. So you've got to take out that acid. It shifts in the acid range, shifts toward the acid side. Or lower pH. Now, I'm going to work the same problem where we put in OH, and you'll see it shift the other way, where the pH will go up toward the more basic range. That's all buffers do the same thing. All right. Okay. So let's say we're given the 50-50 HOAC NaOAC buffer, and we've got the same Ka values and everything. So you want to add 0.01 molar in hydroxides this time and see how that affects the shifting, the tilt and the shift and all that using the seesaw, right? Okay, so I'm going to start with the seesaw, and then we'll build the ice table to show the change. And so we start with our balanced equation on the seesaw. Like this. Move that up. Hopefully you got the notes on the first one. Right there. Now, what we're going to do is we're going to add 0.01 molar in hydroxides from some outside source. And that has to be removed. How do we get rid of, how does the chemistry get rid of that excess OH? Well, what happens if you put in this excess, what's going to happen is it's going to combine with the hydrogen. And that's going to form H2O. That essentially removes the hydronium ion from the first equilibrium. And you think, I'm going to draw this twice. And you have nothing right there. The seesaw person got off. So what happens? If it's going to go off, it's going to tilt left. Like that. Right? Okay, so now we have HOAC, and we've got to shift back to the right to add the new hydronium ion, and it's going to continue to keep a void there until all of the excess OH is removed. And this will keep shifting to the right until that H removes, it delivers more H to the right side until all of the excess OH is gone. And so we have that taking place, and then it will continue until we establish our new equilibrium again. Now, what happened in the transition here? Well, if we tilt left and shift back to the right, then this is going to go down in concentration. The acetic acid goes down in concentration, and your acetate is going to go up in concentration. So that's how you have to apply it in the change. And that's how you have to apply this, you plus and minus 0.01 in that change row when you set up your ice table, so that it shows a reduction in acetic acid and an increase in the salt concentration, and then you calculate the new hydronium ion concentration based on the final equilibrium row. Okay, so 0.10 molar and 0.10 molar, and we assume that we're starting at zero and going to make a new equilibrium concentration of hydronium ion. Now, if we add in that 0.01 molar hydroxide, we tilt left, okay? And then it's going to shift right, meaning that when it shifts to the right, this has got to go down. So that means we have to take that 0.01 molar out of this side and add it to the right side this time. And that will give us the new hydronium ion concentration based on the chemistry shifting to the right. And that's a 0.09 molar on the left side this time, 0.11 molar on the right side. And again, we take the Ka equals H, OAC, HOAC, and we solve for the new hydronium ion concentration when we substitute the equilibrium row in here. So that would be Ka, HOAC, and the acetate, like that. So H plus nu is 1.8 down 10 to the minus 5. The 0.09 molar here cancels with 0.11 molar there, and it all comes out in moles per liter, whatever that comes out to be. I get 1.47 times 10 to the minus 5 molar. This is your new hydronium ion concentration. So the new pH after adding the 0.01 hydroxide is now relative to that hydrogen. And we have a 4.83. And we start with a 4.75. So it moves more basic. So the rule is if you add excess acid to a buffer, it'll shift the pH in the acid range. So when you work through your problem on the test day, you want to be sure it's going in the acid direction if you add an acid. And you want to be sure you finish on the base side if you add a base. Okay, so typically you are making a buffer in the laboratory, and you'll be given, say, a alkaline base in one bottle and a ammonium chloride solution in a second bottle, and they're both 0.1 molar, and so you will measure out 20 milliliters of each one into a beaker, okay, and then you apply whatever excess acids and bases that you're going. But you got to figure out what the original solution concentrations are. So in this, you have 20 milliliters of 0.10 molar ammonium hydroxide plus 20 milliliters of 0.10 molar of the ammonium ion. I'm running out of room, so I'll just stop with that. Chloride's a spectator ion. It's not entering into the reaction at all. So when you mix these two, what's the total volume now? 40 milliliters. So you calculate moles of the ammonium hydroxide and the moles of this, and then you divide by 40 mils in liters. And so now there's your molarity of the two solutions. So this is 0.02 times 0.10 mole of the ammonium hydroxide plus 0.02 times 0.10 mole of the ammonium ion. And so that is a 0.002 mole NH4OH plus 0.002 mole of the ammonium ion. Like that. CZD. My bad. I'm sorry. And it's still going to be 50-50 mix, and it's still going to be Ka equals hydronium ions in that. Okay, so now you have NH4OH going to ammonium ions plus hydroxide, and if you're going to start your buffer, you've got a 0.05. That is now what you use in that row, and you have 0.05, and you start with a 0. Now what do you want to add? Well, if you add 0.05 acid and 0.05 acid, it's going to kill the buffer. That's what I was saying earlier. Buffers limit changes in pH when acid and base is used. So you'll always have the H or OH way less than what the concentrations of conjugates or acid and bases are. So let's say we throw in some acid this time. What's going to happen? So you throw in some H plus. Well, in this case, it's going to have to be taken out using the OH. And so it shifts to, I'll just do this way. So what you'll wind up with is an NH4OH initially. I'll put it down here. Equals NH4 plus, that's gone now. Well, let me put the OH and put it in the next row. So you have 0.05 and 0.05, and you're trying to take all this out. Trying to take that out. So if this is gone, if you remove this from the equilibrium, it's going to tilt left, shift right. To like this. Now once you apply this, you know it's going to shift right. So this, when you apply your equilibrium row and then your change, you know you have to subtract it to the side that went down, and you have to add it to the side that went up, and then you calculate a new OH concentration and calculate POH, pH, and on that. that way. And it will still shift down in the pH number by adding the acid. Now, you go ahead and try to finish this one. If you run into a problem with it, send me a note or bring it to class next time. We'll try to straighten it out. But the idea of buffers and buffer systems is a big part of chemistry in the analytical end of research.